Hello everybody, today we're going to prove the fact that the shortest distance between 2 points in a flat space is a straight line. This principle is really important because all of Euclidean geometry is based off of this fact, and you could think about it surely that if you have 2 points then the shortest distance is surely a line, but how can we mathematically prove it? And that's what I'm going to do in this video using calculus of variations. So let's start by defining what a geodesic is. A geodesic is the shortest possible path between 2 points in a surface. In this case, the surface is a flat space, so we're looking for the geodesic in a flat space between 2 points. So what we're going to do is imagine 2 points A and B in a flat space, right? There are infinite paths between A and B, and you want to find the path that takes the shortest. But how can we analyze infinite paths? Well, with calculus of variations. Okay, so first to do that, let's imagine some arbitrary path between points A and B. Let's say maybe it goes like this, okay? And we're going to zoom in on some point, right? And there's going to be a little change in the arc called ds, infinitesimally small change in the arc. And if we keep making it smaller and smaller and smaller, then that is going to look like a straight line once we make it infinitely small. And that means we can integrate from a to b ds, and that would be the distance. Yay, that's our functional. But wait, we can't do anything with it because there's no function in the middle and it's ds. So what we can do is we can use the Pythagorean theorem to change this into something we can work with. So imagine there's this part of the curve ds on the infinitesimally small level, and that's the hypotenuse of a triangle. The two legs are dy and dx. Using the Pythagorean theorem, dx squared equals dx squared plus dy squared. And we can use this as ds equals the square root of dx squared plus dy squared and substitute it into the integral. And now what we can do is the inside of the radical, we can divide it by dx squared and multiply the outside by dx. So if we do this, we did dx squared over dx squared is 1 and dy squared over dx squared is dy dx squared. And now this is a functional that we can try and minimize, and the Lagrangian in this case would be the square root of 1 plus dy dx squared. We can use the Euler-Lagrange equations, yay, to minimize this. Let's find both terms and then plug it into the equation, and then we can find out which path minimizes it. Hopefully it'll be a line. Okay, dl over dy is the derivative with respect to y of the square root of 1 plus dy dx squared. And since nothing here depends directly on y, it only depends on dy dx, which also depends on y, but there's no y by itself in here. So all of this is just a constant, so it's 0. Now we're going to do the second term, d over dx of dl dy dot. Y dot is the derivative of y with respect to x. We can use the chain rule to find this derivative. The derivative of a square root of some variable would be 1 over 2 times the square root of that variable, and then we multiply by the derivative of the inside. The derivative of the inside, the 1's just a constant, so it's just 0. And I'm just going to use y dot instead of dy dx. It's 2 times y dot. This is multiplied 1/2 times the square root of the variable. That's the derivative of the whole function. And then just 1 plus y dot squared. And then the 2's cancel. This is our derivative. The derivative with respect to x of dy dx over the square root of 1 plus dy dx squared. We're not actually going to calculate the derivative with respect to x. What we're going to do is we're just going to plug this back into our Euler-Lagrange equation. We get that 0 minus d over dx dy dx over the square root of 1 plus dy dx squared all equals 0. Now what we're going to do is we're going to multiply both sides of the equation by -1 first. It turns into a positive. This stays 0. We can multiply both sides by dx now. I'm just going to use y dot again. We can integrate from a to b of both sides of this. And the integral of 0 with respect to any variable, that's just a constant at the top bound minus a constant at the lower bound. And that's just another constant. We're going to have c as any generic constant. The dx is canceling here. There's y dot over the square root of 1 plus y dot squared. So we're going to square both sides of the equation, right? So then we'd get y dot squared. And then that lets us get rid of our radical. Then a constant squared, that's just another constant. We can multiply both sides by the denominator of 1 plus y dot squared, and we get that y dot squared equals, so I'm going to distribute the constant over 1 plus y dot squared. We get the constant plus the same constant times y dot squared. So now I'm going to subtract c from both sides. That way we can get rid of this c. And I'm going to subtract y dot squared. So now we have all the y dot squared terms on one side. And negative a constant, we're just doing generic constant, so that's just another constant. Constant equals, so I'm going to factor out y dot squared times c minus 1. Constant minus 1 is just another constant. I can divide both sides by c, and they're not the same constant anymore because we've done like different things. They're just both generic constants, so c divided by c, constant divided by constant, just another constant. And we can take the square root of both sides, and we get dun dun dun. The square root of a constant, again a constant. Y dot constant. The slope is constant. And what has a slope that's constant? A line. Yay! If we integrate with respect to x, right, because this is y dot, y equals c1x plus c2, because c1x from the c and then another integration constant, that's our answer to this whole problem. And which line is it? Well, if we go back here, we have these 2 points A and B. What is the only line between them? If we have a bunch of lines that can start at B, only one of them is going to reach A. And of all the lines that can start at A, there's infinity, only one's going to reach B. So it has to be this line, you know, with the slope of change in y from A to B over change in x from A to B. So that's our answer. The shortest possible path between 2 points on a flat surface, the geodesic, is a straight line. Of course, Euclid just thought of this in his brain, thought of the fact that if you make any deviation to curve it, then you're adding distance, so it must be a straight line. But now we can mathematically prove it. Thank you for listening.